Thanks for all the subs, comments, and likes. It really motivates me. I really appreciate it. Thanks. And also Happy New Year. So in the last video, I showed you guys I computed the gradients up to DODC3. We have to continue computing gradients up to kernel 1. But in the last video, it was up to here. So next we want to compute DC3 by DC3Z. In this case, the ReLU was involved, so it would look like this. Multiply DODC3 by derivative of ReLU, and input for the derivative of ReLU is C3Z, because input for ReLU here is C3Z also. Next, the C3Z respect to kernel kernel 2. What would it look like? So essentially you'd have to compute convolution again. Yeah, it's weird because we're computing gradients and we have to compute convolution again. And for the parameters for this convolution is, the image or the input and the kernel. So for the kernel, it would be DODC3Z, we just calculated. And for the image, it would be S2, because respect to kernel 2, you'd get S2 if you follow the derivative rules, or the rules for the calculus. And this is the test for computing DOD kernel 2. So we have to slice S2 and DODC3. In the real code, these would have shapes like this, and this is the batch size. For the test, I chose batch size of 3. What would this slice function do is that it would turn them, it would slice them into single batch. So for this, this image only contains single batch from this S2. So this image would have shape of 1, 6, 14, 14. But this kernel 1, 16, 10, 10. Because I'd have to compute convolution using single batch from each DODC3 and S2, and you pass them into convolution and you sum the results. So essentially I compute 60,000 convolutions and sum them up, and that would be the DOD kernel 2. But this, I'm gonna talk about this later, but if you're training in batches, this would be 32, 64, and 128, and so on. Yeah, so that's the, and yeah, that's how you would compute up to kernel 2, and I have to go a little bit more to finish the backpropagation part. Next, I started training in batches finally. The reason is that when I train my model for the test purposes, because every time I started working on backpropagation, I trained the model to make sure he would output proper loss, but before I was getting NAN for the loss, and I thought I was training my model using full batch. MNIST dataset, size of MNIST dataset is 60,000, and I was training my model using batch size of 60,000, which is absurd. So I decided to make a code that would train a model in batches. So first I calculate number of batches by dividing the number of dataset by batch size. I chose 64 for the batch size, and we loop through number of batches except for last index for the loop. We just slice the dataset into number of batches, so these X and Y would contain 64 batches of dataset each, and for the last index, for the last loop, I would calculate the remainder by modding the dataset by batch size. In this case, I would get 32. So for the last loop, or for the last batch, I would get batch size of 32. So except for the last one, the batch size would be the batch size I chose, so 64, but for the last batch, the batch size would be 32. I guess this was the reason I was running away from training in batches, even though it seems not big. It doesn't seem big deal, but yeah. But anyway, the reason I was getting NAN for the loss was not because I wasn't training in batches. The reason was gradient. The model was experiencing gradient exploding. So the gradients was getting bigger, like this big. I forgot how to pronounce, but yeah, the gradients was getting so big. The reason was before that I was using value for all the activation functions, even though for the original model it uses sigmoid functions, and rel would just gives you back the input you passed unless the inputs are less than 0. So if inputs were like 100, it would gives you back 100, and so I was getting numbers like this big, and if you pass this big number to softmax, it gives you back NAN, and if you pass that to loss function, it would also output NAN, so that's why I was getting NAN for the loss. But yeah, now these also have to be sigmoid, but yeah, I think it was pretty annoying because I was already getting NAN when I was computing gradients for gradients of DLD W2. So, and this things always happens, but yeah, I'm glad that I fixed it. So as you can see, I started making tests because this convolution and max pooling could be used for other data sets other than MNIST. And these are pretty complex functions, so I'd have to test to make sure that things are working correctly. So it's pretty common to make tests, but I wasn't really like the idea, but that is also absurd. But yeah, and also I organized my files inside examples and docs because by making folders which are like computer vision, natural language processing, reinforcement learning, which I haven't started yet. But yeah, it makes my folder looks neat. So yeah, I guess this is it for today's video, and I hope I would finish implementing this model, because now it's taking quite long. Yeah. Okay, I guess this is it. Thanks.